For introduction, the orifice coefficient experiment is conducted to study the flow of fluid through an orifice, which is a small opening located at the side or bottom of a tank. Orifices are commonly used in engineering applications to measure or control fluid flow. Although Bernoulli's equation provides the theoretical velocity and discharge, the actual flow is affected by energy losses due to friction and contraction. Therefore, the velocity coefficient, contraction coefficient, and discharge coefficient are determined to obtain more accurate results. These coefficients help evaluate the flow characteristic and the actual discharge through the orifice. This experiment also compare the theoretical and experimental flow behavior to improve the understanding of real fluid flow. The findings are important for the design of hydraulic structure, pipeline, and water distribution system, supporting reliable infrastructure development SDG 9. Next, for objective, first, to determine the coefficient of discharge, CD, coefficient of velocity, CV, and coefficient of contraction, CC, for water flowing through an orifice. Second, to measure the water jet trajectory using probe in order to determine the actual velocity of the water jet. Third, to compare the theoretical and actual value of velocity and flow rate using Bernoulli equation and study the effect of different water heat on this parameter. Problem statement: the actual flow of water through an orifice is different from the theoretical prediction because of energy losses caused by friction, turbulence, and jet contraction. Therefore, the discharge coefficient must be determined experimentally to improve the accuracy of theoretical calculation. Since orifices are commonly used to measure and control fluid flow in hydraulic system and pipeline, accurate value of the discharge and velocity coefficient are required to ensure reliable flow measurement. The flow rate through an orifice is influenced by factors such as the water heat and the geometry of the orifice. This experiment investigates this effect to provide a better understanding of orifice flow characteristics and support effective hydraulic design.
The basic concept of this experiment is based on the principles of fluid dynamics, which study how fluids behave when they are in motion. When water flows through an orifice, its velocity is affected by the size of the opening. According to the discharge equation, the flow velocity is inversely proportional to the orifice diameter. This means that as the diameter of the orifice increases, the velocity of the water decreases. Understanding this relationship is important because it explains how the size of orifice influences the flow characteristic of the fluid.
First, set up the orifice apparatus, then start the pump. Next, adjust the flow rate using the delivery valve until the water level reaches the maximum height. After that, ensure the water level is steady before taking any measurement. Next, adjust the needle and the profile gauge until they just touch the water jet. Then, clamp them securely in position. After that, record the distance from the central line of the orifice to the tip of the needle. And then open the batch valve and use the ball valve to measure the time required to collect 5 liters of water. Repeat the experiment at a different flow rate by adjusting the delivery valve. So this is the result that we get from the conduct experiment. We use two different manipulative variables, which is different diameter and a different head level. Now, I will explain about the calculation. For the first sample result we get at diameter at orifice 0.004 meter, it head equal to 0.025 meter. For the actual flow rate Q, we use formula Q actual equal to volume over time. And then we substitute volume equal to 0.005 per width 9.88 second, and then we get Q actual 5.06 multiplied by 10 power of negative 4 m cube per second. So before we search for theoretical flow rate, we need to find the area of orifice. So we use area equal to pi d square over 4. And then we get 1.25 multiplied by 10 power of negative 5. And then we substitute into theoretical flow rate formula, which is Q theoretical equal to area square root of 2G head. And then we get 8.75 multiplied by 10 power of negative 6 m cube per second. So before we search for find the coefficient of velocity, we need to find the slope. So for the slope, we use the graph. And then we find the slope by gradient. So for the gradient, we get 0.42 minus of 0.07 over 0.420 minus 0.158. So we get slope equal to 1.3359. And then we substitute into the CV formula, which is slope over square root 2GH. And then we get 0.6032. So for coefficient of discharge, we use formula coefficient of discharge equal to Q actual over Q theory. And then we substitute the amount we get before, and then we get coefficient of discharge equal to 1.45. Okay, that's all from me. Thank you.
For discussion, the results show that increasing the water head from 0.25 meter to 0.35 meter increased the water jet velocity and horizontal jet distance. This is because a higher water head provides greater pressure and potential energy, which is converted into kinetic energy as the water flows through the orifice. The 8mm orifice produces a higher discharge than the 4mm orifice because the larger opening allows a greater volume of water pass through within the same time, resulting in higher flow rate. The experimental value was slightly lower than the theoretical value predicted by Bernoulli's equation. This difference is because of friction, turbulence, viscosity, and jet contraction, which create energy losses during the flow. The calculated coefficient of discharge, coefficient of velocity, and coefficient of contraction represent these energy losses and help improve the accuracy of theoretical calculation for real fluid flow. The experiment successfully achieved its objective by determining the hydraulic coefficient and comparing the theoretical and experimental result. The overall trend agreed with fluid mechanics theory, confirming the relationship between water head, velocity, and discharge. These findings are important in the design of hydraulic structure, pipeline flow measurement device, irrigation system, and water distribution network. Accurate coefficient value help engineer improve system efficiency, reduce energy losses, and support reliable infrastructure developed in line with SDG 9.
The experiment successfully achieved its objective by evaluating the flow characteristic of water through an orifice using the jet trajectory method across different water heads 0.25 meter and 0.35 meter, and orifice diameter is 4 mm and 8 mm. The result demonstrates that a higher water head increased the actual horizontal trajectory distance, confirming that greater initial potential energy yields higher velocity at discharge. Furthermore, the discrepancies observed between the experimental jet profile and theoretical expectation validate that actual fluid flow is inherently subject to energy losses caused by friction, turbulence, and jet contraction. Therefore, determining empirical hydraulic parameters, specifically the coefficient of discharge, velocity, and contraction, is essential to accurately calibrate Bernoulli equation for reliable hydraulic engineering and system design.